Good evening, Internet. I am Matt Buyak, and in this video, we'll look at the 11th problem from the Project Euler problem archive. So in this problem, we're given a grid of numbers, 20 by 20, and we're asked to find the four adjacent numbers such that the product is maximized. And we're told that these numbers can appear either vertically, horizontally, or diagonally. Now this problem is pretty straightforward. The search space is small enough that we can just start with the first element and scan all the way down to the 400th element, and for each, check each of the 8 directions and see which has the greatest product. There are just 2 points of note that I would mention. The first is that if we're searching from the right, for example, from the first element, that's exactly the same as searching from the left from the 4th element. And so we don't actually need to search all 8 directions. We can get away with searching just 4 directions. The other point of note is that if, for example, we are searching left to right, starting at the 19th element, we'll run off the edge of the grid. And so we have to be careful not to do that in our code. Otherwise, we'll almost certainly either crash or have some kind of incorrect result. So with that in mind, let's get into it. Now, I've already created our problem directory and put together this input.h file to save us a little bit of time. You can see that this is a 2-dimensional array. I don't know that this has come up in my series so far, but this is basically just, instead of a linear arrangement of integers, this is a grid of integers made of 20 rows of 20 columns each, which is exactly what we need. And so with that in mind, let's jump over to our main.cpp file and get started. So as I mentioned, we'll want to iterate over all of the rows and columns starting at the top left and moving down to the bottom right. One thing to be aware of is that if we go back to our input.h here, the first row here is the top row. And so we might be used to having a y coordinate that increases going upward and decreases going downward. But it's actually the reverse in this case. The origin effectively is in the top left at element 0, 0, and we move increasing to the right as usual, but then also increasing downward. So that's something to note. Something else is that the first index refers to the row and the second to the column. So effectively, the y index is first, followed by the x index. And so that might also be unexpected. So let's create some variables for tracking our coordinates here. Obviously, x and y. You'll note that I've used a signed integer here. This is so that we can perform bounds checking. I'll explain that more in just a little bit. We'll also want to be able to check multiple different directions. And so let's say in 32t directions, there's going to be 4 of them. We have 2 coordinates for each, and those are going to appear as, let's see, 1, 0, and 1, 1, and 0, 1, and 1, negative 1. And we probably don't want to hard code this here, so let's do const static uint32t num directions equals 4. And we'll just do that like so. And so then we'll probably also want our current direction. We'll want to keep track of the best or largest product that we've seen so far. So we might have Kerr score and best score. I think that's probably enough to get us started. So let's go for y equals 0, y is less than 20, plus y. For x equals 0, x is less than 20, plus x. For direction equals 0, direction less than num directions, plus direction. We'll also want to initialize our best score to 0. We want to end all of our loops. And now we want to check to see if for the current x and y values, if pursuing this direction is going to lead us out of bounds or not. So let's see. Let's add dx and dy. So those are going to be the direction, for x and y that we're going. So we'll say dx is equal to direction 0, and dy is equal to direction 1. And then we'll say, let's see, if actually let's break this out into a separate function. And so what we'll do is, let's see, if out of bounds x plus 3 times dx, y plus 3 times dy, then continue. So I don't think continue has come up yet in this series either. That will just immediately finish the current iteration of this loop and jump back to increment direction and then continue on with the subsequent iteration, which is what we want. If we find that we're going to go out of bounds, we want to just move on to the next possibility. Okay, so then we'll want to say our current score is 1, and we'll need say let's see, for let's see, I is 0, I is less than 4, increment I. And then we'll say Kerr score times equals input, and it's going to be x plus I times dx, y plus, oh, excuse me, this is the point that I mentioned earlier that we need to be cautious about, that we actually put the y coordinate first. So we say y plus I times dy, x plus I times dx. And then we'll say if Kerr score is greater than best score, then best score equals Kerr score. Okay, so now we just need to implement this out of bounds function that should be fairly simple. We'll just say bool out of bounds x and y. Oh, I hit my caps lock. There we go. Y, and we'll just say return x is less than 0, or x is greater than or equal to 20, or y is less than 0, or y is greater than or equal to 20. So I mentioned earlier that I had specifically chosen to use signed integers for our coordinates rather than unsigned integers. And that's because if, for example, we went off the top of the grid, that would mean our y-coordinate was negative. But if we were using unsigned variables, then you can't actually go negative. It just wraps around to a very large positive number. And so this check, for example, where we say y equals, is less than 0, would always be false. And so we would miss certain failure cases. And so that's why I chose to use signed integers instead. Okay, so that should be our solution. So now we'll just print out best score is equal to best score. And we'll go to our problem directory and make. It appears we have some mistakes. Just a transposition. Oh, I changed the name there. And I did not include input.h. Okay, so that gives us the answer 70,600,674. So if we pull up the archive here and go to the solution, we will see that our answer is correct. Now, in this problem, we used a very common technique, which is to iterate over all the possibilities and score each one, and then determine which one has the greatest score. And that's a very common reoccurring theme in a lot of these problems. And so in the next video, I want to take our solution to this problem and generalize it a little bit so that we have some code that we can reuse to solve the same sort of idea for other problems. So there will be a part 2 to this problem, and so you can look forward to that.